Yeah. It's probably not going to be the ACS one because it has to be remote. Well, then, okay, hello everyone. All right, I'm going to spend a few minutes going over the test. Okay, let me share my screen. And okay, so the first one is this bicyclic compound. Okay, this is named as, let me make it a little bit bigger, bicyclo, square bracket, and 3 in this bridge, there's 2 in this bridge, and then there's 0 in this bridge. So it's 3, 2, 0. And then altogether there's 7, so this is heptane. Okay, the numbers are actually separated by periods rather than commas, and then we go in descending order. So it's 3, 2, 0, not 2, 3, 0, but I didn't take off for that. Okay, it's largest to smallest. All right, the next one. Okay, this is a spiro. And it would be 3, 2. And again, we separate these with a period rather than a comma. And it's largest to smallest. And this would be hexane.
I don't think I'll get people like looked up videos and like, oh, it's finally done to me.
All right. Let me scroll up just a little bit here. Okay. Okay, so this one right here. Okay, the parent is cyclohexane. And it would be 1 ethyl, 3 isobutyl, cyclohexane. Okay, we want to give these the lowest set of numbers. Ethyl is listed first. Okay, the one after that, I didn't give any examples of chlorine substituents in class, so that wasn't counted as far as scoring. Most of you got it right still. Okay, so the parent compound is 1, 2, 3, 4, 5, 6, 7, so that's heptane. And okay, this would be 2, 4, 4, 5, 5. We went this way. This would be 3, 3, 4. Okay, so let's go this way. And it would be, I'm going to go ahead and go over this one anyway, even though it wasn't counted. So it'd be 3,3-dichloro. And we have 3 methyls. So that is 4,4,6 trimethyl. And it would be heptane. Okay, and then the last names from formulas. Okay, we want to use the lowest set of numbers. I didn't count off for this, but there were a lot of answers that said 1 tert-butyl, 3,3-diethyl. It should be 1,1-diethyl. And it's 3 tert-butyl. Cyclopentane. Okay, draw the structures of these. Okay, so cyclobutane is a 4-membered ring. And we have an ethyl and an isopropyl. Okay, so ethyl and isopropyl. And make them trans. Okay, you could do something like this. Okay, where one's forward and one's back. Okay, we could also draw it like this. Okay, so that would also be trans. Okay, 1 tert-butyl 2267 tetramethyl octane. Okay, so octane is 8. Four tert-butyl and 2267 4, 6, 7 tetramethyl octane. Okay, I think most of you got this right. A couple of answers drew it as cyclooctane. You lost a point for that if you drew it as a ring. Yeah, it doesn't say cyclo. Okay, bicyclo 321 octane. Okay, you do something like this. Okay, here's your 3, here's your 2, here's your 1. And then spiro 5,3 nonane. Okay, 1, 2, 3, 4, 5, and then 3 this way. Okay, the next part, it was 1 point for the correct structure and 1 point for the correct name. Okay, so 1,4,5 triethylpentane. Here is pentane. 1,4,5. Even though that's a totally wrong name, you can draw a structure from it. The longest chain is actually not pentane, it's 2, 3, 4, 5, 6, 7, 8, 9, so it's nonane. And the shortest distance to this substituent is 4. So this is 4-ethyl nonane. Okay, and then the parts A and parts B and C, sorry, those are numbered incorrectly. Okay, so cyclopentane. And I said it was 1, 2, 3, 3. 2, 3, 3. Okay, so I can draw a structure based on that incorrect name. The numbering is incorrect. It should be 1, 1, 2, 3. Okay, we want to use the lowest set of numbers. Okay, and then part C is also numbered incorrectly. So we have octane. Okay, so there's octane, and it is 4-ethyl 6,6,7 trimethyl. 4-ethyl. 6,6,7. Okay, 6, 6, 7. Okay, we actually want to start numbering from this side. So 1, 2, 3, 4, 5. So this would be 5-ethyl. And it would be 2, 3, 3. And then the rest of the name, trimethyl octane. Okay, fractional distillation separates different products based on boiling point ranges, difference in boiling point ranges. Catalytic cracking is a process of breaking larger molecules into smaller ones. Since there's a greater demand for gasoline and in some cases heating oil, there's a greater demand for the smaller molecules. Okay, cyclopropane is more reactive than other alkanes. Okay, 2 reasons. One is bond angle strain. Okay, because an equilateral triangle has angles of 60 degrees. That's a large distortion from the ideal of 109.5. The second reason is torsional strain because the hydrogens, adjacent hydrogens, have to be eclipsed. Okay, number 6. Okay, why is the boiling point of water much higher than that of hydrogen selenide? Okay. Oxygen and selenium are in the same family of the periodic table, while selenium has a higher molecular weight, but hydrogen bonding is the factor. Water exhibits hydrogen bonding, and you had to say hydrogen bonding in your explanation. Okay, which one has a higher boiling point and explain? It is octane. If you chose 2,2,4 trimethylpentane, it was no credit regardless of the explanation. Okay, so octane has a higher boiling point. There's greater surface area in contact between molecules of octane, And so there's more opportunities for London dispersion interactions. There were several incorrect answers that said that octane has a higher molecular weight or it has more carbons. That's not correct. These are isomers. Okay, they have the exact same molecular weight, same molecular formula. Okay, which is the stronger acid? Okay, for part A, it is hydrogen selenide. That's based on periodic trends. If we go down a column, for similar species, acidity goes up. Okay, water and methane, that is also based on periodic trends. As we go across a row for neutral species, acidity goes up. And for part C, okay, a conjugate acid is always more acidic than its conjugate base. So that is the relationship between the two. We have conjugate acid on the left, conjugate base on the right. Okay, so when we have a polyprotic acid, okay, it takes more effort to remove the second proton than it does the first. Okay, there is very little difficulty with number 9. Formal charges. Okay, this nitrogen has a plus charge. This oxygen down here has a minus charge. The nitrogen in the middle has a plus charge. This oxygen has a plus charge. Boron has a minus charge. Okay, almost everyone got that one right. Okay, here we have a line angle formula. Lone pairs and some of the hydrogens are omitted. Okay, for this ether group, there's 2 lone pairs. So the electron pair geometry is tetrahedral. So this is sp3. And it'd be about 109 degrees. Okay, this next one, there is a hydrogen, which is implied here. That's sp2, it's a trigonal planar, about 120 degrees. Okay, same way with this one right here. That's sp2, 120 degrees. Okay, principal functional groups. There were a few papers that didn't realize that some of these had more than one functional group, so they just circled one. That was the biggest source of error, I think. Okay, this one right here, that's a carboxylic acid. This one, we have an ester. Part of it's an ester. And this is an alkene. Okay, here we have an alcohol. This is an alkyne. And then this is an arene or aromatic. Right, this is an amide, okay, where we have a nitrogen next to a carbonyl. This is an amine. Okay, here we have an ether. This is an aldehyde where there's an H, and then over here, this is a ketone. We have 2 carbons.
Which one did you say the NHO one was?
This one here?
Yeah.
Amide, A-M-I-D-E. That's an amide. Okay, number 12, some of these had more than one correct answer. Okay, so a nitrile containing containing 3 carbon atoms. And nitrile has a CN triple bond. Secondary amine with 4 carbon atoms. If you didn't draw a secondary amine, I did give you some slack on that. Okay, here's one possible. That'd be a secondary amine. Here's another. That would also be a secondary amine. Nitrogen's directly bonded to 2 other carbons. And then there's more possible correct answers.
So we didn't have to put the entire move formula, move structure as our answer. We could have just put like that.
Yeah, you could do a line angle formula. Okay, and then a compound containing an alkyne and a carboxylic acid. Again, I didn't specify how many carbons. Okay, so this would be one possibility. Okay, and you could have extra carbons. And this is an alkyne, this is carboxylic acid. Okay, which ones have a 0 dipole moment? Okay, this one would. Okay, since the dipoles cancel each other out. And you also have hydrogens here that are slightly pushing for the carbon. And of course, these would cancel each other out as well. So that one would have a 0 dipole moment. Okay, what about this one? No. Okay, these don't cancel each other out. Right? And then dichloromethane. Okay, this actually has a tetrahedral geometry. So this one does have a dipole moment, non-zero dipole moment.
Didn't you specify that the biggest molecule is on top?
What?
Didn't you specify that the biggest molecule is on top? Shouldn't the CO be on top?
Are you talking about Fisher projection?
No, for
No.
this, the tetrahedral structure, shouldn't the CO be on top?
Specify that the biggest one is on top. For this one,
Yeah.
I don't think I understand the question.
I mean, like, shouldn't the bond that's pointing straight upwards, shouldn't that be a CO?
Oh, well, it could be, but
Then would it not be
actually it would, because see, these are 109.5 degrees apart from each other. See, they wouldn't cancel each other out. Okay, because of the tetrahedral geometry. Okay, so that one would not. Okay, carbon dioxide would. Okay, because even though the CO double bond is very polar, these 2 bonds cancel each other out. This is formaldehyde. Okay, it would not have a 0 dipole moment. The dipole would be in this direction. Okay, this one. What about this one here? Yeah, that would have a 0 dipole moment. Each CF bond is canceling each other out. Okay, what about ammonia? Okay, ammonia would not because, again, tetrahedral geometry because of the lone pair. Ammonia is a polar molecule. Okay, these are all sp hybrid atomic orbitals. And so the geometry here is linear. This one was missed by several. This one is completely linear. The CN bond is a very polar bond, but then you have another CN bond on this other side. So yes, that would also have a zero dipole. Okay, and then the last one, the most stable chair conformation of cis-1 tert-butyl 3-ethyl cyclohexane. Okay, so a tert-butyl group is so large that it has to be equatorial. Okay, so you could draw it something like that. And then the other group is an ethyl. And then, okay, so both of these would be equatorial for it to be cis. Okay, so this is a possible answer. That was worth two points. If you drew a chair with a tert-butyl and an ethyl, you got 1 point for that. If you drew the groups axial, you lost a point for that. If you drew some other group other than ethyl or tert-butyl, okay, you lost a point for that. Okay. All right, so I'm going to go ahead and exit this file. And then pick up where we left off with K5 lecture. This is what I want. Okay, we'll pick up where we left off with stereochemistry. Okay, just a comment about the title slide, and that is, you'll notice the spiral pattern on these snail shells. It turns out that in nature, most of these shells have a clockwise spiral rather than a counterclockwise. Okay, let's go back to where we left off. Okay, biological discrimination. Again, this is an important reason why we study chirality, asymmetry in organic molecules. Okay, racemic mixture is one that is exactly 50-50 of two enantiomers. Okay, racemic mixture does not rotate plane polarized light. Okay, the individual enantiomers in this case S plus and R minus butan 2-ol, have equal and opposite rotations, but if we have a 50-50 mixture, the polarimeter measures 0. Racemic mixtures are designated as parenthesis DL and parenthesis or plus minus. Okay, racemic mixtures may have different boiling points and melting points from the individual enantiomers. Okay, this is a general principle of organic synthesis, and that is that if all of our starting materials are achiral, we cannot produce a chiral product mixture. Okay, so in this example, we're producing a new stereocenter, but we obtain both of these in equal amounts, so it's a racemic mixture, so it's optically inactive. Okay, one of the ways that you can get around that is to use you can use a chiral catalyst that will actually, in many cases, favor one stereoisomer over another. Let's see. Okay, chirality of conformers. I'll go ahead and go over this again. If two forms are in rapid equilibrium, we'll look at the most symmetric form. Okay, so if these 1,2-dibromo cyclohexane isomers were frozen in place, they would actually be non-superimposable. But what happens is they actually equilibrate back and forth. And so on average, this is optically inactive. We have a plane of symmetry, which divides the molecule. Okay, here we have a case of non-mobile conformers. Okay, there's no identifiable stereocenter, but this is asymmetric about a line rather than a point. Okay, because of the large size of the iodines and the bromines, these cannot rotate past each other. And if you were to make a model of this and this, you could prove that they are non-superimposable. Same way with allenes, where we have two double bonds right next to each other. Okay, we can have chirality in allenes, as in this example. Okay, Fisher projections. Fisher projections represent a flat representation of a 3D molecule. Vertical groups are back. Horizontal groups are forward, as shown here. The highest priority functional groups, okay, in this case it's an alcohol, go up at the top. We draw the carbon skeleton vertically. So this specifies a particular orientation. That is, it's equivalent to the structure in the middle. Okay, because of the way we draw this, okay, notice here hydrogen is forward. The Fisher projection is usually backwards when we're trying to figure out R and S. Okay, not always. You always have to check, but most of the time it's going to be backwards. Okay, if we were looking at this molecule trying to determine R and S, we would want hydrogen back. Instead, we could reorient it, or we could look at the priorities. This OH is 1, CH2OH is 2, methyl is 3. Okay, that looks counterclockwise, but we're looking at it from the wrong direction, so it's actually R. Okay, so the carbon chain is on a vertical line. The highest oxidized carbon is at the top. So if you have a carboxylic acid or an aldehyde, that goes up at the top. If you have a ketone, that goes closest to the top, if that's your main functional group. Okay, rotation of 180 degrees in the plane does not change the molecule's configuration. Rotation of 90 degrees, though, is not allowed. Okay, for a fissure. Okay, so here this illustrates 180 degree rotation. Okay, if we go end over end, if we bring this one down here to the bottom, okay, it's still the same configuration. Okay, but we're not allowed to do a 90 degree rotation because that will actually change it to the other enantiomer. Okay, this is a molecule called glyceraldehyde, and this was one of the molecules that was studied by Fisher, Emil Fisher, back in the early 1900s. Okay, glyceraldehyde, R plus glyceraldehyde, which is the naturally occurring isomer, has this configuration. Okay, Fisher determined that it rotated light in a clockwise direction, hence the plus. Now it turned out, okay, how did he know it was R? Well, he just guessed, and he guessed correctly. Okay, but it turns out, as we saw, some R molecules have a minus rotation and some have a plus rotation. Fisher formulas actually make it easy to draw enantiomers or mirror images. Okay, so here, in order to get the enantiomer, okay, all we have to do, we have two stereocenters. This one at carbon number 2, this one at 3. And to get the enantiomer, we have to switch both of those. Okay, so the enantiomer would have the top chlorine on the left, the bottom chlorine on the right. Okay, so the lowest priority comes forward in this example, so the assignment rules are backwards. Okay, so both of these are S, and the enantiomer would have both of these as R. Cis and trans isomers are considered diastereomers. They are not mirror images. They're not enantiomers either, and so they fit the definition of diastereomers. Okay, we can have cis-trans isomerism in rings. Okay, here is trans. Okay, these two isomers of trans 1,2-dimethyl cyclopentane, these are enantiomers. Okay, I cannot superimpose these. If I flip this over and try to line up all the groups, they won't line up. So these are different molecules. They are non-superimposable mirror images. Okay, notice what I've done here is instead of changing both of these stereocenters, we change just one. Okay, then we go from trans to cis. Okay, these are now diastereomers. Okay, they're not mirror images of each other. Okay, what about cis-1,2 dimethyl cyclopentate? Does it have a mirror image? Okay, well, everything has a mirror image except the vampire. And this one does have a mirror image, but it is identical to the original molecule. Okay, so this one has a mirror image, but it does not have an enantiomer. Okay, so it is achiral, and the reason given here is it has this plane of symmetry. Okay, this half is a reflection of that half. Okay, whenever you have a plane of symmetry, it can't be chiral. Okay, so diastereomers are not mirror images. Okay, in this case, we have two pairs of enantiomers. Okay, these are all optically active. These are mirror images of each other. These are mirror images of each other. Or wait a minute, sorry. Yeah, these are not mirror images. Okay, because we changed one configuration, but not the other. So we go from SR to SS. Okay, so these are diastereomers. Okay, so if you have multiple chiral centers and you change some of them, but not all of them, then you get diastereomers. Okay, you have to have two or more chiral carbons to have diastereomers. And you have to have two or more chiral carbons to have meso compounds. Okay, back here, the cis isomer is what we call a meso. Okay, it's an achiral diastereomer. Okay, and it's achiral because of that plane of symmetry. That's the most common reason. There are a couple of other reasons that a meso could be achiral, but most commonly it's a plane of symmetry. Okay, enantiomers have opposite configurations at each corresponding chiral carbon. Diastereomers have some matching and some opposite configurations. Meso compounds will have internal mirror planes. All right, the maximum number of isomers is 2 to the nth, where n is the number of chiral carbons. Right, so each time we add a stereocenter, we double the number of possible stereoisomers. Okay, so if we have one stereocenter, we have two enantiomers. We cannot have meso or diastereomers if there's just one chiral center. If there are two chiral centers, there are 4 possible. We could have fewer than 4 if, for example, we have a meso, as in this example. Okay, carbons 1 and 2 on the ring represent chiral centers, and so there would be a maximum of 4, but there's only 3. Okay, if we have 3 stereocenters, then there's 8 possible stereoisomers. Okay, and if all of those are chiral centers, we would have 4 pairs of enantiomers. Okay, if we have 4 stereocenters, then 16. Okay, so if we have 2R, 3R, okay, and what that means, of course, is that the configuration at carbon number 2 is R, and at number 3 it is R. Okay, if we invert both of those, then we've got enantiomers. If we invert one but not the other, then we have diastereomers. And these are enantiomers of each other because we took this one and we inverted both of these. Okay, I think this will be the last slide. We're just about out of time. Okay. Okay, this is a general description of isomers. Okay, these are all constitutional isomers up here in the left upper corner. They have the same formula, but a different skeletal structure. Stereoisomers will have the same configuration. Substituents are all on the same positions, but the three-dimensional shape is different. Okay, so one category of stereoisomers is enantiomers, okay, or we can have diastereomers. Cis-trans isomers represent diastereomers, and compounds with two or more chiral centers can be diastereomers. Okay, I'm going to stop there, and I will see you on Wednesday.